Good morning, students. Please ask your friends to join the class. Am I audible? Roll number 7194. Am I audible? 74, 71, 94, 106. Okay. Okay, let's wait till your friends join this class. Okay, today. Okay, let's wait till they join the class. Only 1, 2, 3, 4, 5. Only 5 students join the class. एक मैसेज कर दो ग्रुप में. Please give a message to your friends. Okay, among you, Oro, Christina, Ruposhri, 94, 90, 71, 74. Any doubts from previous classes? Any doubts, any issue? Today we'll study about stability of column. Okay, we have not done many problems on 4 conditions of column stability. Right, there were 4 conditions for column stability. So today we'll see that some problems on based on that formula. That formula is called Euler's formula, right? So based on that formula, we'll solve some numericals today for different end conditions. So till others join, go back to your previous classes or see the conditions, 4 conditions for your stability of columns. Recall your classes. Let's wait or 2-3 minutes for others to come. Till then, the rest of the students can interact with me. Only 12 students, what happened? I'll start the class then. Second sessional, I don't know. Please follow the curriculum. Okay. We have not received any notification, and last time also we received notification one day before. So follow your routine or some that something is uploaded, right? Some curriculum means session activities uploaded in your website, I guess. So follow that because we got notification on the day before exam. So follow that. Anyways, Let's start our class. It's already been 5 minutes and only 12 students joined. Let me share the video. Let me know. Let me share my screen. Okay. Let me know if it is visible or not. So let's start with what is column buckling. Okay.
Which column is most likely to buckle?
Visible?
A pin
Audio
connection on
video is
both
okay?
ends, and this little signal here means it's a pin connection. So you can picture it like a rod being held between your fingers. That's a pin connection. Okay.
So this is saying about the buckling. Okay. So let's start with
Which
that.
column is most likely to buckle? A pin connection on both ends, and this little signal here means it's a pin connection.
Here we'll see different types of end conditions with the practical applications. Okay, so first study what are the different. Let's recall. Actually this is a revision class. So let's see what are the different end conditions for the columns. Okay.
So you can picture it like a rod being held between your fingers. That's a pin connection. You can kind of pivot. A moment connection on one end and free or no connection on the top. A moment connection on both ends, and a moment connection would be more like a rod being held in your fist. Go ahead and hit pause. The answer is this one, the moment connection on one end and free no connection on the other. So this is a little bit counterintuitive, but there are different ways to brace a column. And we have pin connections, we have moment connections, we have free connections, which are a little bit more unusual, and we have ones that are allowed to translate right to left, and we'll get to those. So if a column is going to buckle, we need to figure out not only the strength of the column and the length of the column, but the type of connection at the top and the bottom is going to kind of govern its likelihood of buckling. Now we're looking at a table, and here you have just different flavors of column. So in A, you have fixed up top and bottom. On B, you have a pin connection at the top and fixed at the bottom. On C, you have something that's a rotation fixed but translation free on the top, and something that's rotation and translation fixed on the bottom. On D, we have two pin connections. On B, you have something that's fixed on the bottom and allowed to kind of move around at the top. And then on F, we have something that has a pin connection on the bottom and translation on the top. Now, what we're going to need to do when we do the calculation, when we kind of figure out likelihood of buckling, we're going to have to run through a formula, and I'm not going to get into the formula right here, but in that formula, there's a value of what's called K. And that K value, you look up on this table to determine its likelihood of buckling. And a higher K value means a higher likelihood of buckling, because in the formula, you're going to take the length of the column and you're going to multiply it by K. So in this one right here, we're going to take the length of the column and we're going to multiply it by 1/2. We're going to multiply it by 0.5. That means from a buckling point of view, this column of, say, 10 feet will behave more like a column that's only 5 feet. If we look at this one here, if we have a column that's fixed on the bottom and it has a pin connection on the top and it's 10 feet long, in terms of its likelihood of buckling, we're going to multiply it by 0.7, so a 10-foot column will look more like a 7-foot column when we size it for buckling. And then this is kind of our baseline. We have pin connections at the top and the bottom, which means that it's rotation free and translation fixed. And that's our 1. So then if we have a 10-foot column, it's going to really behave like a 10-foot column. But look at these two here. These two have a theoretical K value of 2, which means that we're going to have to take a 10-foot column if we have one of these, and it's going to behave like a 20-foot column. So we're going to multiply it by 2. Now, right below that theoretical K value, there's another line that says recommended design value when ideal conditions are approximated. And that basically means we're talking about wood. So the theoretical K value can pretty much work if we're talking about something like steel, that's pretty consistent, maybe even concrete that's pretty consistent, but wood is kind of weird. It's got knots and it's got wanes and checks and cups, and no piece of wood is perfect. No two are the same. So in this case, we're actually, in some of these situations, we're going to have a slightly larger recommended K value for wood.
So in day-to-day life, we have n number of conditions. Okay, these are the different conditions. Suppose this is from here, it will be both end will be fixed, and this kind of beam, one will be fixed and one will be hinged. Okay, here one will be fixed. Here this is also a fixed beam, but the rotation is restrained. Here this is hinged, but rotation is not restrained. Okay, like this is totally free kind of beam, and this one will be restrained against rotation. This part will be restrained against rotation, not translational movement, and this will be free. Okay, but you just need 4 basics. For the time being, you need to know 4 basics. This conditions you will get in your design classes by Junaid sir. So for this curriculum, you just need 4 conditions. Okay, both and fixed, one and fixed, and one and is free, both and hinged. Okay, then there will be one and fixed and one and hinged. Okay, so for this part, your effective length will be completely L. Okay, for this one, your effective length LE will be L by, let me just give me a minute. Effective length is represented by LE. So for this condition, your effective length will be L by 2. Okay, and for one end fixed and one end free, for this your effective length will be twice of L. Very important from your future exam point of view also. You should know these conditions. Okay, let me add some students there in the, okay. So for this condition, your effective length will be L by root over 2. So these 4 are the basics, and you should know, and you just remember. Okay, this usually comes in your competitive exam. So the main formula of crippling load is, or you can say Euler's load is pi square EI by L square, right? For this L square, you have to use this condition. Based on the condition given to you, you have to replace this L by these lengths. If you have been given, in the question it is given the both ends are hinged, so you have to use the same L, because effective length is same L. Whatever is the length given, that will be your effective length. Next, if the condition is given that both ends are fixed, then you have to do. Suppose the length is given 3 meter, you have to take 3 by 2 here. Okay, and here E is the Young's modulus, I is the moment of inertia. Okay, and if the condition is given that one end is fixed and another end is free, you have to use L equals to twice of L, like that. Okay, hope this part is clear. So those who joined newly, I'm saying we are doing the revision class of the column stability. Okay, we'll solve some numericals also. Many students are coming now. Let me add them. Okay, so those who joined newly, so this is a revision class of column stability. The main formula for finding the crippling load, or you can say Euler's load, is pi square EI by L square. Okay, and we have discussed 4 conditions, right? Based on those 4 conditions, you have to solve. Based on those 4 conditions, you have to find out the p value. Okay.
So let's go through examples of what we mean by rotation fixed and translation fixed and so forth.
So these are the 4 main. These are the main 4. Let me.
Examples of what we mean by rotation fixed and translation fixed and so forth.
So see this symbol here, your rotation fixed and translation also fixed. Okay. Here your rotation is also fixed and translation means up this side by, and rotation means this turning. So in this symbol it shows that your rotation and translation both are fixed, and in this type of support your rotation is free and translation fixed. Okay, you this kind of beam, that it can move, it can rotate, but its translation movement is fixed. And in this kind of symbol, rotation fixed and translational free. Here you can the support is resisting the rotation movement, but it can move sideways. And here both is free. Rotation is also free, translation also free. Understood?
So this is a moment connection. We
So
saw
these
this
are the
before
practical
when we talked about
examples with
steel.
the
You know it's a moment
life.
connection because we've engaged the flange and the web, and we're holding both of them in place. And so that would be a rotation fixed and translation fixed. It's not going to slide up and down. It's not going to rotate. This is what we called a shear connection before. This one is what we would, in the language of that chart we just looked at, that table we just looked at, we would call this rotation free and translation fixed. It's not able to slide up and down, but even though there are 3 bolts there, it is actually able to kind of pivot, because at the scale of the building, those 3 bolts are really kind of like a pin. Then we have rotation fixed and translation free. Go ahead and hit pause. And
Yeah. Just give me.
try to determine where we use that kind of connection. It's in seismic. So remember we talked about buildings kind of sliding back and forth. And you'll note that we talked about structures in all kinds of other places, right? We talked about it certainly in steel, but in other places as well. So these are the seismic isolations that are under, in this case, under the Utah State Capitol. If we want something to be able to slide back and forth, that's going to be something we're going to call rotation fixed and translation free. So it can't pivot, but it can translate right to left. Finally, we have our rotation free and translation free. And certainly, of course, a flagpole comes to mind. You know what kind of works with this at this level? It's kind of rare, and it's not very common in buildings. We sometimes will see it if we have like a single column for a highway overpass. That may behave like something that is rotation free and translation free. Now, I just gave a in-person seminar at AIA New York, and one of the participants in that seminar asked, what about a really tall, slender building? Would that kind of behave at the scale of the building? If you were worried about buckling for the building, would that kind of behave in this way like a flagpole? And the answer is kind of yes, but in practice, the buckling would not be the biggest issue. In other words, you'd be much more concerned about other things. So the buckling for a tall building, first of all, buildings aren't quite that tall and slender like a flagpole. And secondly, there would be other factors for the building that would require beefier structure, and it would be unlikely that buckling would control. But yes, same principle. Which column is most likely to buckle? A pin connection on both ends, and this little signal here means it's a pin connection. So you can picture it like a rod being held.
That was about the column buckling. Okay, now let's solve some problem. Okay, just give me a minute. Okay, till I share my screen, please write your roll numbers in the chat box, okay? I'm facing some issues, so till then, please write your roll numbers in the chat box. I think there is some network issues. Okay. I'm not able to share the screen. I don't know why. Please, all of you write your roll numbers. Those who join newly, please write your roll numbers, okay? Okay, let's start in the, let's solve the problem in, okay. It is visible? How is it is visible? Please respond screen is visible?
Yes.
Okay, so this is a fixed, both and fixed, okay, both and fixed kind of problem where your length is given, which is 3 meter, The dimension of the rectangle section is given, it is 20 mm, and this B is 40 mm. Okay, then elastic modulus is given to you, which is 200 GPa. Then there's some yield stress is also given, 250 MPa, and there is a factor of safety is given. So first what we do, we'll find the P value. Okay, we'll find the P value. So in P value, what is the formula? Pi square EI by E, let me change E, this is EI by L square, right? And the both hand will be, I think both hand is hinged. Let's see. So based on so we have to see, we have E, we have L, what we need I. So we will find the I. What is I? I is your moment of inertia. And for rectangular section, what is the I value? This is BD cube by 12 along one direction, and another direction it will be DB cube by 12. Is it or not? So as I have discussed earlier, I have told you earlier that go through the moment of inertia if this part is not clear. So okay, let's see the problem first, then I will discuss it again.
Basically just want to figure out what is the critical load, and then what is our allowable load based on our factor of safety here. We want to check it against buckling. In this case, this column can buckle in two directions. We have to check both of those. And we also want to make sure that it's not going to yield, the material won't yield before it buckles. So looking at this, we have a three-dimensional column here. And we're talking about this as pinned joints, a pin on each end. So we'll basically treat these as ball and socket joints. So they're able to, basically this pin, it's like a pin in 360 degrees. But because this rectangular cross-section has kind of two distinct ways it can buckle basically in the YZ plane. So sort of as we're looking, it's left, it can buckle from left to right or right to left, like that way. Or it can also buckle in the XZ plane. So basically going kind of into the page that way, or kind of out of the page that way. So basically what we need to do is we need to first figure out what our effective length is. Now in both, considering both planes it can buckle in, it's considered to be pinned in both of those directions. So our effective length, no matter how we look at it, is going to be just the actual length of the column because it's that pin connection. Now that came from the previous videos where we're talking about different end connections, but in the next videos we'll do different examples. So for now, effective length is equal to the length where we have pin-pin connection on this column. Alright, the next thing that we need to do is we are going to be using this expression here that is, we're going to be looking for the key grit, the critical load that's going to basically be where the column is going to have the tendency to buckle, so that is equal to, that is pi squared EI over LE squared. So we need to figure out what the moment of inertia is, and because we have this rectangular cross section, we're gonna have to figure out two different moments of inertia depending on which way we're thinking about this column buckling. So for the moment, we're gonna use we can calculate. Let's calculate it up here. So for now, let's do it down here. I'm really indecisive right now. So for IY, basically the moment of inertia about the y-axis here, this is going to be equal to 1/12 times b times a cubed, right? Because when we're looking at this about the y-axis, this a, if we normally think about this as 1/12 base height cubed, this a kind of becomes our height. So we can plug in the values and we get 0.0267 times 10 to the negative 6 meters 4. And then we can also find the moment of inertia about the x-axis, which is what we're going to be using for buckling in the xz plane. And we find that to be equal to 0.1067 times 10 to the negative 6 meters 4. So now we have everything we need to find the critical load in buckling in each plane, basically in the YZ plane and the XZ plane. So let's go and plug those in. So we have P crit. Let's consider buckling in the YZ plane first. And again, YZ basically could buckle that way or it could buckle that way. So we just need to sub in that we have pi squared E. And in this case, we're using IY. Right, the moment of inertia about the y-axis, and then this is over LE squared. So if we just plug that in, we're going to find that in the YZ plane that P crit is equal to 5.9 kilonewtons. Then when we check for P critical in the XZ plane, we're going to have to basically just redo this expression. So we have P crit in the XZ plane, and that's just going to be equal to pi squared EI, and this is with the subscript x because we're looking at the moment of inertia about the x-axis now. And this is over LE squared. So we're just going to find that that is equal to 23.4 kilonewtons. And now what we want to do is we just compare the two different critical loads. So we have for buckling in the YZ plane.
So see, so critical load or crippling load is pi square EI by LE square. So as this is not, this is a rectangular section, so there will be moment of inertia along the x direction, that will be A, this along this direction. This is x, right? Let me draw. This is x, right? So along this will be, this is this A is perpendicular, A is in this direction and B is in perpendicular to this x, so it will be B cube along the x, A B cube. Okay, and if you see the y along y direction, y is parallel to B, so that's why B cube, sorry, B, and A is perpendicular to this y. Understood or not? See, this is from your earlier classes, but let me tell you. See this, if you see this x direction, this A is parallel to this x, right? That's why it is not in cube, but this B is perpendicular to this, like this is x, this is B, so this x is this B is perpendicular to, this is x, this is B, so this B is perpendicular to this x, that's why it is B cube. Okay, along the x-axis, moment of inertia along the x-axis. Now if you see moment of inertia along the y-axis, y is in this direction, B is also in this direction, but A is perpendicular to this y, that's why A cube, B A y cube. So you find out the moment of inertia along the y-axis, moment of inertia along the x-axis. Once you have find out the moment of inertia along both the axes, then what you have to do, you have to find out the crippling load. Okay, pi square EIY L square and pi square EX L square. So the load which will be lesser, you have to take that load. Okay, understood? Find out the IX, IY, then find out the pre-critical along the x-axis and the y-axis, and you have to take the lesser value.
The critical load is 5.9 kilonewtons, and for buckling in the XZ plane, our critical load is 23.4 kilonewtons. And intuitively, this makes sense. The skinny, basically, we're saying that we need a smaller load here to make a buckle in the direction that has basically a smaller amount of material basically around that axis. So if we applied, let's say 6 kilonewtons, then we will have crossed this threshold and we're most likely going to be getting buckling. So 5.9 kilonewtons is the value that we have to take for P critical for the whole column. Now, if we want to use that, we can figure out our allowable load if we set our factor of safety up here as 2.5. So basically we can just say that the, if you remember, the factor of safety is equal to the ultimate load over the allowable load. And if our ultimate load for buckling is 5.9 kilonewtons, then all we have to do for allowable load is that's going to be equal to 5.9 kilonewtons over 2.5. I'll write that a little bit cleaner, 2.5. So our allowable load for buckling with this factor of safety of 2.5 is going to be 2.36 kilonewtons. So that's something to watch out with these problems, is typically you're always going to have to check for buckling in two directions and then take the smaller value, and then if you're talking about factor of safety, like maybe your professor's only asking for you to calculate P crit, but if you're looking for the actual allowable load, then take that factor of safety into consideration. The one other thing that we can check with a column problem is,
so here you can find your allowable load. Okay, factor of safety is given, you have to take the lesser value, then divided with the factor of safety, you will get the allowable load. Now you can also check that which one will buckle first. Means this column will fails by yielding or buckling. You can check. Okay. So for that, the next step is for checking that the column will fail due to buckling or yielding. Okay.
It's possible that the column buckles before it yields, or it's also possible that the column yields before it buckles. So if we want to just quickly check that this column won't yield before it buckles and that this is in fact our true allowable load, then what we just need to do is if we come back up to the top here, the yield stress was 250 megapascals for this particular material. So if we know that, let's just write this in. So we have yield stress is equal to 250 MPa. Now we know that stress is equal to force over area, right? So this is equal to the applied load over the area. Now our cross-sectional area is going to be, if we do that up here, we have area is going to be equal to base times height, basically the cross-sectional area. So 20 millimeters times 40 millimeters, that is 800 millimeters squared. So we'll bring that down, and we'll be basically just calculating for our yield load here, the load that will cause yielding. So just multiply area to that yield stress, and we're going to get this expression here where we have that yielding load is going, or the ultimate load basically, is going to be equal to 250 MPa times, and you know what, I like to write out the units like this, so 250 times 10 to the 6 newtons per meter squared times that area, which was 800 millimeters. That's also just 800 times 10 to the minus 6 meters squared, so those meters are going to cancel out. The value that we're going to get is just 200,000 newtons. 200,000 newtons, which is equal to basically 200 kilonewtons. Alright, so if we take, this is our yield, this is our ultimate load. If we just check again using the same thing, factor of safety is equal to allowable over ultimate, then that means that our allowable load for yielding is going to be equal to just 200 kilonewtons divided by 2.5, and that's going to give us a value of 80 kilonewtons. So we're definitely going to buckle before that. If we apply 5.9 kilonewtons, then we're most likely going to buckle. And that's that's important to look at, because if you look at this column, it is quite long, right? It is 3 meters long, and it's very slender. So it's a very slender column, and very slender columns are very prone to buckling. So in this case, it will definitely it will buckle in the YZ plane before it buckles in the XZ plane and before it yields.
So that's what about. So in the next class we'll solve another problem. Okay, don't leave the class. Just give me a minute. Those who joined lately, please write your roll numbers. Okay, in the chat box. Those who have not wrote their roll number, please write your roll number in the chat box. Those who joined newly, please write your roll number in your chat box. And those who left, to write your roll numbers in the chat box. Anyone left to write? Okay, last was 118. Okay, please join the class after 10 minutes. Thank you.